Hi all. So far we have discussed two different kinds of spectroscopy, rotational spectroscopy and vibrational spectroscopy. From this lecture we are starting Raman spectroscopy. The first thing you want to know is the Raman effect. Raman effect is the light scattering phenomenon. When light falls on a matter, the light may be absorbed, transmitted, and scattered. Raman spectra is related to the scattering of light. Raman spectroscopy is entirely different from other spectroscopy like rotation or vibration or electronic, as there involves light absorption and emission. Raman spectroscopy involves scattering of light. So, the Raman effect can be illustrated as when an electromagnetic radiation having intensity I0 and wavelength lambda is incident on a molecule, the scattered radiation definitely has a different intensity IS, but the wavelength of scattered radiation can either be same as that of the incident light or different from that of incident light that I have denoted as lambda prime. The scattering of light with unchanged wavelength is known as Rayleigh scattering. When there is a change in wavelength, it is known as Raman scattering. Raman and his student collaborator K.S. Krishnan made the discovery of this phenomenon in 1928, which gave birth to the field of Raman spectroscopy. India celebrates National Science Day on 28 February every year in honor of physicist C.V. Raman's discovery of the Raman effect, which gave Asia its first Nobel in the sciences. It was the first Nobel Prize in Physics for an Indian scientist also. Now, let us look into classical justification of Raman effect. The scattering of light may be thought as the redirection of light that takes place when an incident ray encounters an obstacle. The obstacle may be solid, liquid, or gas. By Coulomb's law, when an electric field is hit on the molecule, the electron and the nucleus respond by moving in opposite direction, and the perturbation of electron cloud results in a periodic separation of charge within the molecule. It is called the induced dipole moment. That is, the electric field induces a dipole moment in the molecule, which results in scattered light. The majority of light scattered in the same frequency as the incident light, which is referred to as elastic scattering. However, there were a scattered light having different frequencies, which is due to inelastic scattering. This scattering is referred to as Raman scattering. The strength of the induced dipole moment, mu induced, equal to alpha into E, where alpha is the polarizability factor and E is the strength of the applied electric field of the incident light. The polarizability is a characteristic of the molecule that depends on the molecular structure and nature of bonds. This was the classical theory of Raman scattering and was not perfect. So they developed a quantum model for explaining Raman effect. In the quantum theory of Raman effect, we consider light as a photon and have quantized energy. If we represent the interaction of a photon with matter, it will be like M1 plus photon giving M2. M1 is the matter in the initial state and M2 is the matter after the collision. Here M1 is having energy E1, M2 having energy E2, and the photon has energy h nu. By the law of energy conservation, E1 plus h nu equal to E2, that is E2 minus E1 equal to, I have made a mistake, that is E2 minus E1 will be h nu, or delta E will be h nu. We discussed about this important equation in spectroscopy, where the delta E expresses the property of matter and the h nu gives the property of light. We can explain Raman scattering in a similar way that M1 plus photon 1 giving M2 plus photon 2. Again, let's say we have a photon of energy h nu 1 interacts with a matter having energy E1, and after the collision, the photon scatters with energy h nu 2, and the matter now possesses a different energy E2. Again, considering the energy of conservation, we can write E1 plus h nu 1 equal to E2 plus h nu 2, or h into nu 1 minus nu 2 equal to E2 minus E1. There may be three cases happen during this process. In the first case, the matter goes to higher energy level during collision. That is, the matter absorbs the energy of photon, and after collision, the matter gains energy. In this case, we can say that the frequency of scattered radiation will be less, or in other words, the wavelength of the scattered radiation will be longer than the incident light. In this case, the scattered light gives rise to stope lines. But when we have an opposite case where E1 greater than E2, that is, the radiation takes up some energy from molecules, then the frequency of scattered radiation will be higher than the frequency of the incident radiation, and the spectral line obtained can be called anti-stope line. There is a third case where there is no change in the energies of matter or photon during collision, and the frequency of incident and scattered radiation are same, and this type of scattering leads to Rayleigh lines in the spectrum. It can also be described that we can have an initial state. From this state, the molecule goes to a virtual or intermediate state, and from this it goes to final state. Here, the initial and final states are stationary, and the transition to the final state occurs through an intermediate state which is non-stationary. We can illustrate this pictorially. So, let's say we have an initial state I, a final state F, and also a virtual state V. And a light is incident with energy h mu1. So, from the initial state, the molecule comes to the virtual state. However, it is not come back to the final state, but the initial state itself. So, the energy released h mu2 will be equal to that of h mu1, or the frequency of incident radiation and scattered radiation is the same, and this case we called it as Rayleigh scattering. But there is a chance that the molecule going to the virtual state come back to the upper state. In this case, the energy of the excited or emitted scattered radiation has less energy than the incident light, or frequency of the scattered radiation is less than the incident radiation, which is known as Raman scattering, and it gives rise to Stokes lines. There is another case where the molecule is initially in the upper state, promoted to the virtual state by taking energy h mu1 and come back to the ground state. For this case, the scattered radiation h mu2 having higher energy than h mu1, or mu2 will be greater than mu1, and this type of scattering is also a Raman scattering, and it leads to anti-Stokes lines in the spectrum. Thus, Raman spectrum of a molecule consists of Stokes lines and anti-Stokes lines situated symmetrically about Rayleigh lines. The Rayleigh line is far more intense than the Stokes line, which in turn have greater intensity than anti-Stokes lines. As the anti-Stokes lines correspond to the return of a molecule from the excited state to the ground state, and initially there were very few molecules in the excited state, the anti-Stokes lines are very difficult to observe in the conventional Raman spectroscopy. By this, I am concluding this lecture about introductory Raman spectroscopy. In the coming session, we will deal how the rotations and vibrations in a molecule will be active in Raman spectrum. Thank you very much.